What would happen if a rogue planet entered our solar system? Even without a collision, a sufficiently massive rogue planet passing near the solar system could theoretically alter the orbits of distant bodies, with the scale and permanence of those changes determined by its mass and trajectory. A planet with no star could pass through the solar system quietly, yet still leave long-term effects behind. Rogue planets are not hypothetical objects. Astronomers have confirmed their existence by detecting planets drifting through interstellar space, unbound to any star. These worlds are formed when young planetary systems become unstable. Gravitational interactions scatter some planets outward until they escape entirely, becoming solitary travelers between stars. The solar system is not isolated. It moves through the Milky Way surrounded by stars, gas, dust, comets, and interstellar debris. Objects from beyond the solar system have already been observed passing through the Sun's vicinity, including interstellar asteroids and comets. A rogue planet would be far less common, but it remains within the realm of possibility. This scenario matters because gravity governs the structure of planetary systems. Planets follow stable paths because gravitational forces remain balanced over time. When a large moving mass enters the system, that balance can shift. Even small disturbances, if sustained, can lead to meaningful changes over long time scales. The first sign of a rogue planet would not be visual. Large objects influence their surroundings well before they arrive. Astronomers would detect subtle irregularities in the orbits of distant objects, particularly in the outer solar system. Infrared telescopes could also identify the faint heat emitted by the planet, even if it reflected little or no sunlight. As the rogue planet moved closer, its gravity would begin interacting with the solar system's outer regions. This includes the Kuiper Belt and the far more distant Oort cloud, vast reservoirs of icy remnants from planetary formation. These regions are only loosely bound to the Sun, making them especially sensitive to external gravitational forces. The effect would resemble a large vessel passing through still water. Nothing would be destroyed immediately, but ripples would spread outward. Some icy bodies would be shifted into new orbits. Others could be redirected inward, becoming long-period comets traveling toward the inner planets. From there, broader gravitational reshaping could occur. The extent of this reshaping would depend on the rogue planet's size, speed, and path. A planet comparable to Earth would have limited influence unless it passed very close. A planet with a mass similar to Jupiter would exert a much stronger effect, even from a greater distance. As the rogue planet passed through, it could slightly modify the orbits of the gas giants. These changes might appear minor at first, but gravity operates cumulatively. Small orbital adjustments can grow over thousands or millions of years, gradually altering the architecture of the system. Encounters involving Jupiter or Saturn would be especially significant. These planets dominate the solar system's gravitational structure and help stabilize the orbits of inner worlds. Changes to their paths would propagate inward, affecting the long-term behavior of planets closer to the Sun, including Earth. One possible outcome is orbital stretching. Planets could move onto more elliptical paths, causing their distance from the Sun to vary more over time. For Earth, such changes would not cause immediate catastrophe, but could influence long-term climate patterns. Another possibility is orbital tilt. A passing planet could gently alter the angle of a planet's orbit, changing how sunlight is distributed across its surface over long periods. These effects would unfold gradually, measured in geological timescales rather than human lifetimes. In rarer and more extreme cases, a close encounter could eject a planet entirely. Gravity can function like a slingshot. If conditions are right, energy can be transferred from the passing object, sending a planet outward into interstellar space. This process is one of the leading explanations for how rogue planets form. Direct collisions, however, are highly unlikely. Space is vast, and even close planetary encounters typically occur at great distances. Physical impacts between planets are rare events across cosmic history. The primary influence of a rogue planet would come from gravity, not collision. Eventually, the rogue planet would continue on its journey and leave the solar system behind. Depending on its speed and path, its passage could take thousands of years. Long after it departed, the solar system would continue adjusting to the changes it introduced. Some consequences would emerge only much later. A disturbed reservoir of comets could increase the likelihood of impacts over extended periods. Subtle orbital shifts could influence planetary climates far into the future. These are delayed effects, unfolding slowly and without sudden disruption. There are clear scientific boundaries to this scenario. Rogue planets are known to exist, and gravity's role in shaping planetary systems is well understood. Computer simulations demonstrate that passing stars and massive objects can alter planetary orbits under certain conditions. These principles are firmly established. What remains uncertain is the probability. Although rogue planets are common in the galaxy, the distances between stars are immense. The likelihood of one passing close enough to significantly disrupt the solar system is considered low, and no precise estimate can be given. Several misconceptions can also be dismissed. A rogue planet would not suddenly collide with Earth or tear the solar system apart. The Sun would not be ejected from the galaxy, and planetary orbits would not instantly collapse. Gravitational change operates through gradual influence, not abrupt destruction. Another misconception is visibility. Such an event would not necessarily appear as a bright object dominating the sky. A rogue planet could be dark and distant, detectable primarily through careful measurements rather than direct observation. In a broader context, this scenario illustrates both the stability and vulnerability of planetary systems. They are shaped by motion, interaction, and chance, yet they often endure disturbances and settle into new arrangements. The solar system has persisted for billions of years within a dynamic galaxy. A rogue planet passing nearby would serve as a reminder that stability in space is not permanent, but neither is it easily undone. The universe evolves through slow, consistent rules. Even rare visitors leave their mark not through sudden destruction, but through subtle rearrangements that unfold over time.